Our final talk will be given by Talkington with co-authors Hirabayashi, Montalvo, and King. And the talk will be reduction of crater populations greater than 600 to 800 meters in diameter on the walls of the lunar complex craters from mass movement events.
Hi. Okay, so I know that's quite a title.
It's a great title.
Thank you. Thank you. Okay, so as previously said, my name is Lauren Talkington. I'm a current master's student at Auburn University, and this is a bit of my research that I've done over the last year. So as an introduction, we know that craters on the moon are constantly exposed to numerous impact events post-emplacement. And because of this, topographic diffusion is slowly degrading the simple craters by emplacements of smaller ones on top and around them. And we can see the different rates for this in comparing Scott and Amundsen. So these are both complex craters that are found within the lunar southern pole, and they're both around 100 kilometers in diameter. And our initial observations that we can see in Amundsen are the evidence for steep walls, clear rim features, terraces, and a central peak. However, these features are lacking in Scott, as we don't really see the evidence of a central peak or the clear rim features. In addition, the walls are a lot less distinguishable from the floor region. And the observed terraces in Amundsen gave us a pretty important understanding in understanding what happened here post its original emplacement. And we believe these to be remnants of landslides or mass movement events. And this observation was fundamental in our research because we explored how topographic diffusion affects complex crater degradation. And we did this by looking at the crater populations found on complex crater walls. So in our study, we looked at the morphologies of 16 complex craters found on the lunar southern pole to better understand their wall degradation and how it's influenced post-emplacement by meteorite bombardments. So we use LOLA DEM data from the PDS Geosciences node at Washington University of St. Louis. And within the DEM, we collected our data by crater counting along the walls of the complex craters using ArcMap and the Crater Tools add-in. So the first thing we did was add the DEM into ArcMap and used a slope and hillshade overlay so that we could actually see the surface in greater detail. And from there, we started an editing session and created two shapefiles, the first of which defined the wall area and the second the crater counting layer. And within the crater counting layer, we use the 3-point crater counting method, which just uses 3 points that we click around each crater and extrapolates the rim by connecting them. And so once we had our crater counts, we wanted to find the slope conditions for these counts. And the reason behind this was so that if we could see what diameters were found at certain slope regions, we may be able to see some instances of the relative wall strength and find out more about that. So we use the buffer analysis tool as well as the add surface information tool within ArcMap. And what that does is it takes the information from our slope layer that we previously had and can calculate an average slope within that buffer around the outside of the crater rims. And we completed that process for 16 complex craters, equaling 7,905 counts in total, over an average area of 2,205.06 square kilometers. And to make sure that we were kind of keeping our counts pretty equal here over all of our bases, we defined a crater as a circular feature with a central depression. So features that did not fit this, we excluded. So this is an example of what our results look like when we finish crater counting. In contrast to the floor, the walls are sloping. So we had to really stay put and say, okay, this is what we're gonna determine as a crater, this is what we're gonna omit. And in doing that, you can see in the legend here, the wall area defined in blue, as well as the craters themselves. We counted craters from 99 meters to 9 kilometers in diameter. And in addition, the slope variations on the walls are also presented there within the legend. Okay, so to get our results, we compiled the counts and used Python to create some plots just to visually analyze everything. So by just looking at the histogram, it's pretty obvious what the largest crater population belonged to. This is the less or equal to 700 meter diameter craters. And this spin alone had 7,251 craters. In addition, we can see that this range, or these craters range in slope values from very shallow to relatively steep or pretty steep. Whereas in contrast to those greater than 700 meters, there's a much less number of them. There's a lot less of them, as well as they're much tighter constrained slope-wise. And also looking at our CSFD, this is all of the 16 CSFDs that we compiled. We noticed a transition in populations greater than 800 meters, which this is indicated by the two black dashed lines ranging from 600 to 800 meters. Okay, so we also wanted to calculate the shear strength in addition to investigating our landslides here. So shear strength is determined by looking parallel or along the wall surface. And we determined that if we can derive the lower bound of necessary conditions to produce landslides, this is what we would need to take into account. So first, there would need to be a landslide thickness of 180 to 240 meters in thickness, which is also the transient crater diameters for those of that transition we previously mentioned. And next, we would calculate the necessary or shear strength that would prevent the landslide from it even happening. So to do this, we used rho times gravity times height, sine of the slope angle. And we interpreted that since the slope would already be determined before the craters were in place, finding the derived strength would serve us as a lower bound for the production of landslides. And we deduced that the occurrence of landslides themselves, thank you. The occurrence of landslides themselves may serve as the upper bound. Otherwise, the strength would be able to withstand the impacts and the landslide itself would not happen. So using our derived slope strength of 0.5 to 0.7 megapascals, we can interpret that the walls structurally weaken due to the emplacements of the hosting craters and post-dated smaller craters. So the depletion of craters with diameters greater than 600 to 800 meters implies that landslides would be large enough to erase those morphologies. So to determine the characteristics of strength within the gravity and strength regimes, we first need to define a few things. The first is the F ratio, also known as the impactor to crater size ratio. And to make this plot, we assumed that the impactor speed was 15 kilometers per second and that the target density and the impactor density were identical. So the F ratio ranges from 30 to 45 in the gravity regime due to the weaker strength associated with the size ratio. And when F is equal to 10, the strength reaches about 125 to 305 megapascals. Our red line here describes the strength to gravity transition at 1 megapascals. So that is very important pointing out, because if we can determine that the craters found on the walls belong within the gravity regime, this is conclusive with our results that show that there's a larger population of the smaller impacts rather than the larger ones, because these are not capable of producing landslides. So in summary, we deduced that the largest population would belong to the 700 and below, and that this is because they're not capable of producing landslides. We also noticed a transition found at craters with diameter 600 to 800 meters in diameter, and we attribute this transition due to landslide erasure of wall morphologies. We further investigated this transition by using crater counting and impact crater scaling relationships, and can derive the necessary or shear strength, giving us our lower bound for the wall strength at 0.5, 0.7 megapascals. And because of this, impactors capable of forming 600-meter craters did not have enough energy to induce landslides. And the transition we noted is due to the larger impactors having enough energy to induce these landslides and causing partial or total erasure of those cavities. And our calculated shear strength may be 0.5 to 0.7 megapascals, implying variations in the strength in fragmented and unfragmented surfaces. And finally, we determined that if this is the case in furthering this research, we must account for the strength variation due to the presence or lacking of water ice among specific complex craters, and to assess the impactor's physical properties carefully. So some final thanks I would like to give are in support of this project are from the Geosciences Department at Auburn University, and also our research would not have been possible without the use of DEMs from the PDS Geosciences node at Washington University of St. Louis. And thank you all for listening. I really appreciate it.
Thank you. Any questions, please put them in the chat. Catherine Niche has said, nice talk. I think you mentioned that the crater counts on the walls are lower than the surrounding region. Is this because the landslides are covering up smaller craters downhill from the impact?
That is a good question. So I know I don't want to make you like fast type really quick. When you mean the surrounding region, do you mean compared to the floors or the exterior of the wall? Because compared to the floors, there's definitely a much smaller number, both either. Okay. So compared to the floors, I know there's definitely a lot less. So let's make sure I get this. Oh, thanks, Pedro. Let's see. Sorry, I'm getting messages here. Okay, so within the smaller impactors themselves, just being more prevalent, we just noted this just because we see more impactors that are within that smaller range, or more craters within the smaller range on the walls rather than the larger ones. And we just deduced that this would be from these events not having, or these impactors not having enough energy themselves. Whereas if a larger impactor were to come in and hit the surface, it would have a likelihood of covering up its emplacement, and I assume as well other smaller emplacements nearby and around it. But yeah, we're still working as hard as we can on this. But yeah, thank you for your question. I hope I answered it correctly for you.